Welcome to this problem walkthrough. In this session, we'll tackle LeetCode problem number 1658, minimum operations to reduce x to 0. This is an interesting problem that challenges your understanding of arrays and optimization techniques. Let's dive in and explore the approaches to solve this step by step. In this problem, you're given an integer array called nums and an integer x. The task is to reduce x to exactly 0 by performing a series of operations. In each operation, you can remove either the leftmost or the rightmost element from the array, and subtract its value from x. Once an element is removed, the size of the array decreases. The goal is to achieve this reduction of x to 0 using the minimum number of operations. If it turns out to be impossible to reduce x to exactly 0, the function should return -1. To make this more concrete, let's look at some examples. For the first example, the input is nums equals 1, 1, 4, 2, 3, and x equals 5. The output here is 2, and we'll explain why in just a moment. For the first example, we can remove the rightmost element, which is 3, and subtract it from x, leaving us with x equals 2. Next, we remove the leftmost element, which is 2, and again subtract it from x, reducing it to 0. This process takes a total of 2 operations, so the output is 2. Now, let's consider a second example with the input nums equals 5, 6, 7, 8, 9, and x equals 4. In this case, no matter how we try to remove elements from either end of the array, it's impossible to reduce x to 0. Therefore, the output is -1, indicating that the task cannot be accomplished. Finally, let's look at one more example to understand the problem better. The input is nums equals 3, 2, 20, 1, 1, 3, and x equals 10. For this example, we can remove a combination of elements from both ends of the array to reduce x to 0. Specifically, we remove the leftmost elements 3, 2, and 20, and the rightmost elements 3 and 1. Each removal subtracts these values from x, and after 5 operations, x becomes 0. Since this process takes 5 operations, the output is 5. Now, let's discuss the constraints and edge cases you need to consider. The array's length can be as large as 10^5, and the elements in x can also be significant, with values up to 10^4 and 10^9, respectively. This means your solution must be highly efficient, ideally with a time complexity of O(n). Additionally, if the total sum of all elements in nums is less than x, or if x is smaller than the smallest element in the array, it may be impossible to reach 0. Your algorithm must handle these cases correctly and return -1 when appropriate. To tackle this problem, let's first explore the brute force approach. The intuition behind this method is straightforward. We try all possible combinations of removing elements from the left or right of the array. For each combination, we calculate the sum of the removed elements and check if it equals x. If it does, we keep track of the minimum number of operations required. However, there are some key observations to consider. Removing elements from either side is essentially the same as identifying subarrays from the original array. While conceptually simple, this approach involves iterating over all possible prefixes and suffixes, which can become highly inefficient for larger arrays. The time complexity here is O(2 to the power of n, as we are considering every possible combination of left and right removals, and the space complexity is O(1, since we aren't using any additional data structures. Ultimately, this approach is computationally expensive and infeasible for large inputs, such as when the array size can go up to 10,000. To address this inefficiency, we turn to a more optimized solution, the sliding window approach. Here, instead of directly removing elements, we reframe the problem. The goal becomes finding the longest subarray in the middle of the array whose sum equals total_sum x. The idea is that if we don't touch this subarray, the sum of the removed elements from both ends will equal x. Now, let's break down the steps of the sliding window approach. First, we calculate the target sum, which is total_sum x. This represents the sum of the subarray we need to find. Next, we use a sliding window technique to identify the longest subarray with a sum equal to this target. The sliding window allows us to efficiently adjust the size of the window while maintaining a running sum. If we find such a subarray, the minimum number of operations required to reduce x to 0 is simply the total number of elements, n, minus the length of the subarray. If no such subarray is found, we return -1. This approach achieves a time complexity of O(n), because we perform a single pass through the array, and its space complexity is O(1), as we only use a fixed number of variables. Additionally, we also consider an alternative method using binary search. Here, we pre-compute the prefix and suffix sums and store them in arrays. For every prefix sum, we calculate the required complement to reach X and search for it in the suffix array using binary search. This method avoids directly iterating through subarrays and offers some efficiency benefits. However, it requires pre-processing the prefix and suffix sums, which introduces additional complexity. The binary search approach has a time complexity of O(n*(log(n), as we perform binary search for each prefix sum, and a space complexity of O(n), due to the storage of prefix and suffix sums. While it is more efficient than brute force, it is slightly slower than the sliding window approach for large inputs and more complex to implement. Considering all methods, the sliding window approach stands out as the most optimal solution for this problem. It reframes the task to avoid explicitly removing elements, which reduces computational overhead. With a time complexity of O(n), it is well suited for large arrays and simpler to implement compared to the binary search alternative. Additionally, it avoids the need for extra data structures like prefix or suffix arrays, which further enhances its practicality. The sliding window method strikes the perfect balance between simplicity and efficiency. While the binary search approach is valid, it introduces unnecessary complexity, and the brute force approach is simply unscalable. Therefore, the sliding window approach is the clear choice for solving this problem effectively. Here, we're tasked with finding the minimum number of operations to remove elements from either end of an array so that the sum of the removed elements equals a given target, X. The key here is that we can remove elements from both the beginning and the end, and our goal is to minimize the number of elements removed. A crucial observation is that instead of directly working with the removed elements, we can think of the problem in terms of the subarray that remains. Specifically, the sum of the remaining subarray should be equal to the total sum of the array minus X. This allows us to reframe the problem as finding the longest subarray with a sum equal to this target value. By maximizing the length of this subarray, we minimize the number of elements removed, since the removed elements are those outside of this subarray. To get started, the first step is to calculate the total sum of the array, which we'll use to derive the target for the subarray. Once we've calculated the total sum of the array, the next step is to check if it's even possible to achieve the target. If X is greater than the total sum, we can immediately return -1, as there's no way to remove elements to achieve a sum that exceeds the total. Otherwise, we compute the target for the subarray as the difference between the total sum and X. Now, to efficiently find the longest subarray with this target sum, we use the sliding window technique. This method involves maintaining a window defined by two pointers, left and right, which represent the current range of elements under consideration. We also keep track of the sum of the elements within this window using a variable, current_sum. As we expand the window by moving the right pointer, we add the value at arr right to current_sum. If current_sum exceeds the target, we shrink the window by moving the left pointer and subtracting arr left from current_sum. Whenever current_sum equals the target, we calculate the length of the current window and update the maximum length found so far. This approach ensures that we can efficiently search for the desired subarray while minimizing the number of elements removed. The sliding window technique is particularly efficient because it ensures that each pointer moves through the array at most once, resulting in an O(n) time complexity. This linear traversal makes it well suited for large arrays. Additionally, the space complexity is O(1), as we don't use any extra data structures, just a few variables to track the window boundaries, the current sum, and the maximum subarray length. It's important to handle edge cases carefully. For instance, if X is greater than the total sum of the array, we should return -1 immediately. If X is equal to the total sum, it means the entire array must be removed, so we return the length of the array. If X is 0, no elements need to be removed, and we return 0. While negative numbers in the array would complicate the implementation, most variations of this problem assume non-negative integers, making the sliding window technique straightforward to apply. To implement this, we start by initializing key variables, total_sum, left, current_sum, and max_length. As we iterate through the array using the right pointer, we dynamically adjust the window and check for valid subarrays that sum to the target. In this pseudocode, we initialize max_length to -1, which helps us track whether we found a valid subarray. As we iterate through the array, we add the value at arr right to current_sum, expanding the window. If the sum exceeds the target, we shrink the window by repeatedly subtracting arr left from current_sum and moving the left pointer forward. This ensures that the window remains valid and doesn't exceed the target. If the current_sum matches the target, we calculate the length of the current window and update max_length if this length is greater than our previous maximum. After processing the entire array, we check if max_length is still -1, which would indicate that no valid subarray was found. In that case, we return -1. Otherwise, we calculate the minimum number of operations as the length of the array minus max_length. This subtraction gives the number of elements outside the longest valid subarray, which corresponds to the elements that must be removed. This approach is efficient and ensures that we handle all cases correctly without redundant computations. The sliding window approach provides a highly efficient solution, with a time complexity of O(n), because both pointers traverse the array at most once. The space complexity is O(1), as no additional data structures are used beyond a few variables. Let's walk through an example to clarify. Consider the input array 1, 1, 4, 2, 3, and x equals 5. First, we calculate the total sum of the array, which is 11. The target for the subarray becomes 11 minus 5 is equal to 6. Using the sliding window, we start with left at index 0 and current_sum at 0. As we expand the window, we find that the subarray 4, 2 has a sum of 6. This subarray has a length of 2, so max_length is updated to 2. The minimum number of operations is then the total length of the array, 5, minus max_length, 2, which equals 3. Thus, the output is 3, meaning we need to remove 3 elements to achieve the target. This example demonstrates how the algorithm efficiently identifies the solution by focusing on the longest valid subarray. This Python implementation solves the problem of finding the minimum number of operations to reduce x to 0 by removing elements from either end of the array. The solution employs a sliding window approach to identify the longest subarray whose sum equals sum, nums, x. First, we calculate the target as sum, nums, x. If this target is less than 0, it means reducing x to 0 is impossible, and we return -1. If the target is 0, the entire array must be removed, so we return the length of the array. We then use 2 pointers, left and right, to traverse the array while maintaining a current_sum. For each position of the right pointer, we add the current number to current_sum. If current_sum exceeds the target, we shrink the window from the left by incrementing the left pointer and subtracting the corresponding value from current_sum. Whenever current_sum equals the target, we update max_length to the maximum length of the current subarray. At the end, if max_length is not -1, we return len, nums, max_length, which represents the minimal operations needed. Otherwise, we return -1, indicating it is not possible to reduce x to 0. This approach ensures an optimal solution with a time complexity of O(n) and a space complexity of O(1). It efficiently handles edge cases, such as when the entire array must be removed or when no valid solution exists. Here, we start by importing the necessary utilities and defining our solution class. The method min_operations takes an array of integers nums and a target value x. The first step is to calculate the target, which is the total sum of the array minus x. Essentially, instead of trying to remove elements to reduce the sum to x, we flip the problem. We try to find the longest subarray that sums to target. If the target is negative, it's impossible to achieve, so we return -1. If the target is 0, it means we need to remove all elements, so we return the length of the entire array. Next, we initialize 2 pointers, left and current_sum, to 0, and set max length to -1, which will store the length of the longest subarray that meets the target. The for loop iterates through the array using the right pointer, adding each element to current_sum. If current_sum exceeds the target, we shrink the window by moving the left pointer forward and subtracting elements from current_sum until it no longer exceeds the target. If we find a subarray where current sum equals the target, we calculate its length and update max length if the new subarray is longer. After completing the loop, we check if we found any valid subarray. If max length is not -1, it means we have a valid solution, and we calculate the minimum operations by subtracting max length from the total length of the array. This gives us the number of elements we need to remove to reduce the sum to x. If no valid subarray was found, we return -1, indicating it's not possible to achieve the target. This approach efficiently utilizes the sliding window technique to find the solution in linear time, making it optimal for larger input sizes. The final result is returned, completing the implementation. In this example, we're given the array nums as 1, 1, 4, 2, 3, and x is 5. The first step is to calculate the target sum we want to achieve by finding a subarray. The target is calculated as the total sum of nums, which is 11 minus x. This gives us 6. If the target had been negative, it would indicate an impossible scenario, and we would return -1, but that's not the case here. Similarly, if the target were 0, it would mean the entire array is the solution, and we would return the length of the array. With the target established, we initialize the sliding window variables. Left is set to 0 to mark the start of the window, current_sum is initialized at 0 to track the sum of the current window, and max_length is set to -1 to indicate no valid subarray has been found yet. Next, we use the right pointer to expand the window and explore potential subarrays. Starting with the right pointer at 0, we add nums, 0, which is 1, to current_sum, making it 1. Since this is less than the target, we continue expanding. Moving to right equals 1, we add nums, 1, also 1, to current_sum, updating it to 2. Still less than the target, we proceed. When right reaches 2, we add nums, 2, which is 4, bringing current_sum to 6. This matches the target, so we update max_length to 3, the size of the current subarray. As we move to right equals 3, adding nums, 3, which is 2, increases current_sum to 8, exceeding the target. To shrink the window, we subtract nums, 0, and nums, 1, sequentially, updating left to 2 and reducing current_sum back to 6, which matches the target again. Max_length remains 3. At right equals 4, we add nums, 4, 3, raising current_sum to 9. Once again, we shrink the window by removing nums, 2, reducing current_sum to 5. After processing all elements, max_length is 3. The minimum operations are calculated as the total length of nums minus max_length, which is 5 to 3, giving the result 2. In this second example, nums is 5, 6, 7, 8, 9, and x is 4. We start by calculating the target sum as the total sum of nums, 35, minus x. This gives us 31. Since the target is positive, we proceed. The sliding window variables are initialized similarly. Left is 0, current_sum starts at 0, and max_length is set to -1. Using the right pointer, we expand the window to find potential subarrays. With right at 0, we add nums, 0, which is 5, to current_sum. This makes current_sum equal to 5, still less than the target, so we continue. At right equals 1, adding nums, 1, or 6, updates current_sum to 11. Again, this is less than the target, so we proceed. When right equals 2, nums, 2, which is 7, is added, and current_sum becomes 18. Still less than the target, we expand further. At right equals 3, adding nums, 3, 8, brings current_sum to 26. This remains below the target. Finally, at right equals 4, adding nums, 4, 9, increases current_sum to 35, surpassing the target. To adjust, we shrink the window by removing nums, 0, reducing current_sum to 30. Despite this adjustment, no subarray sums to the target of 31. As a result, max_length remains -1, indicating no valid subarray was found. The output for this case is -1. For this third example, nums is 3, 2, 20, 1, 1, 3, and x is 10. We calculate the target sum as the total sum of nums, 30, minus x, which gives 20. Moving forward, we initialize the sliding window variables. Left is 0, current_sum is 0, and max underscore length is -1. Using the right pointer, we expand the window to explore subarrays. At right equals 0, nums, 0, which is 3, is added to current underscore sum, making it 3. This is less than the target, so we continue. At right equals 1, nums, 1, or 2, is added, bringing current underscore sum to 5. Still less than the target, we move on. When right equals 2, nums, 2, which is 20, is added, increasing current underscore sum to 25. This exceeds the target, so we shrink the window by removing nums, 0, and nums, 1, updating left to 2 and reducing current underscore sum to 20. Since current underscore sum now equals the target, we update max underscore length to 1, the length of the current subarray. At right equals 3, adding nums, 3, which is 1, increases current underscore sum to 21, exceeding the target again. To adjust, we shrink the window further. After processing all elements, max underscore length is found to be 1. The minimum operations required are calculated as the total length of nums minus max underscore length, which is 6 to 1, resulting in 5. Therefore, the output for this example is 5. Here, we are analyzing the time complexity of the sliding window solution. The algorithm begins by calculating the sum of the entire array, which takes n time since we need to visit each element once. Then, we use a single for loop to iterate through the array, which also contributes an n time complexity. During this iteration, we maintain a sliding window to track the current subarray sum. Adjusting the window involves moving the left pointer, and since each element is visited at most once while shrinking the window, this process also takes n time in total. When we combine all these steps, the overall time complexity is simply n, as the individual n components add up linearly rather than multiplying. Now let's examine the space complexity of the algorithm. The solution operates in constant extra space because the input array nums is not modified, and no additional data structures are used to store intermediate results. Instead, we rely on a few variables, such as target, left, current underscore sum, and max underscore length, all of which require O1 space. This makes the total space complexity O1. Next, let's explore how the algorithm behaves under different scenarios. In the best case, if the target is 0, the function can immediately return the length of the array in O1 time. On average, the sliding window iterates through the array, which results in n time. Even in the worst case, where every element is processed and the window is adjusted for each, the algorithm still runs in n time. This consistency highlights the efficiency of the approach. Finally, let's compare the sliding window approach with a brute force solution. A naive method would involve exploring all possible combinations of elements from both ends of the array to find the required sum. This approach results in an exponential time complexity of 2 to the power of n, because the number of combinations grows exponentially with the size of the input. In contrast, the sliding window technique drastically reduces this complexity to n by efficiently identifying the longest subarray with the desired sum. It avoids redundant computations by maintaining a dynamic window and performing all operations in a single pass. The key mathematical insight here is that each element is processed at most twice, once during window expansion and again during contraction, ensuring that the algorithm scales linearly with the input size. This optimization makes the sliding window approach far superior to brute force methods for this problem. One of the most common mistakes in this problem is not considering both ends of the array. Since the problem allows removing elements from either the left or the right, focusing on just one side can lead to incomplete solutions and missed opportunities to find valid combinations. Another mistake is relying on a brute force approach, such as using nested loops to calculate all possible sums. This often results in a time complexity of n squared, or worse, which is impractical for larger arrays. Finally, overlooking edge cases can cause significant issues. For instance, if the target value, x, is greater than the sum of all elements in the array, there's no solution, and the program should return -1 immediately. Failing to account for these scenarios can introduce unnecessary errors into your logic. Another frequent issue is off-by-one errors when calculating subarray lengths. These errors often arise from incorrect index handling or subtraction, which can lead to inaccurate results, particularly when minimizing or maximizing the subarray length. Similarly, not optimizing for prefix or suffix sums is a common oversight. Recomputing the sum for every potential subarray window is highly inefficient. Instead, leveraging precomputed prefix or suffix sums can significantly reduce the time complexity of your solution, making it far more scalable for larger input sizes. This problem often comes up in interviews, so it's important to recognize its underlying patterns. It's essentially a variation of the sliding window or two-pointer technique. Identifying this early will help you craft a more efficient solution. Interviewers also tend to test edge cases, such as empty arrays, scenarios where X is unachievable, or arrays with duplicate elements. It's crucial to demonstrate how your approach handles these. Additionally, the ability to optimize your solution is often tested. While a brute force approach may be acceptable as an initial idea, aim to refine it to O(n) complexity using techniques like sliding windows or prefix sums. Finally, clear communication is key. Be sure to explain your thought process as you explore both ends of the array and highlight why your approach is efficient and robust. This problem shares similarities with several other LeetCode problems. For instance, LeetCode 560, subarray sum equals k, uses a similar prefix sum approach to identify subarray sums. LeetCode 1248, count number of nice subarrays, involves sliding windows and counting elements within a subarray to meet specific criteria. Another related problem is LeetCode 209, minimum size subarray sum, which also focuses on minimizing the length of subarrays to achieve a target sum. Finally, LeetCode 76, minimum window substring, revolves around minimizing a window size, making it a valuable reference for understanding sliding window techniques. Familiarity with these problems can deepen your understanding of the patterns and strategies involved. There are several alternative approaches to solving this problem efficiently. The sliding window approach involves using two pointers to maintain a valid window of elements. By expanding and contracting the window, you can adjust the subarray length to meet the target sum. This method is highly efficient with O(n) time complexity, but it requires careful handling to avoid off-by-one errors. Another option is using prefix and suffix sums. By pre-computing these sums, you can use binary search to quickly find combinations that achieve the target X. While this method is faster for querying sums, it has a trade-off in terms of O(n) space complexity. Lastly, a hash map can be employed to store prefix sums and their indices. This allows O(1) lookups to find matching subarrays, reducing computation time for large inputs. However, it can be space-intensive due to the additional storage required for the hash map. Great job following through. We've summarized the problem and key takeaways, including the efficient sliding window approach. Remember to practice more problems to solidify your understanding, and stay tuned for more tutorials. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!